This video will be about examples with separation of variables. Solve the differential equation. So what we're always going to do first is replace y prime with dy over dx. And so then, now we're going to put all the y's on one side, giving us dy over y equals 1 minus x dx. This point will integrate. So we get the ln of y is equal to x minus 1/2 x squared. And I'm just going to put a 1c on this side and leave out the c on the other side. And so now we have e to the power of x minus 1/2 x squared plus c equals y, which can be rewritten as e to the c times e to the x minus 1/2 x squared. And then we can replace e to the c, which is a constant, with another constant. So I'm just going to, again, call that c times e to the x minus 1/2 x squared. Here's another one. So I'm just going to, again, dy over dx equals 2y squared plus 1 times x. This is still pretty easy to separate. So dy over y squared plus 1 equals 2x dx. So now when we integrate both sides, we end up with the inverse tangent of y equals x squared plus c. And so then the tangent of x squared plus c equals y. Here we have a differential equation where we're given an initial value, making this an initial value problem. We're going to do the same thing as before and separate the variables. So dy over y squared equals x minus 1 times dx. Now when we integrate both sides, we get negative 1 over y equals 1/2 x squared minus x plus c on the other. Now to solve for c, we can plug in x equals 0, and that gives us negative 1/2, because we know that y equals 2, equals 1/2 times 0 squared minus 0 plus c. That just leaves us c. And so at this point, I'm going to take this equation here and rearrange it a little bit so we have y alone on one side. So I'm just going to take the entire right side and move it to the denominator. That gives us y on the other side. And now I'm just going to multiply both the numerator and the denominator by 2 so we can get rid of the fractions in the denominator. And that gives us negative 2 over x squared minus x plus 2c. And since we know that c equals negative 1/2, 2c would just be negative 1. And so now we have an equation for y. This example is going to deal with the logistic model. So a fish population has a natural monthly growth rate of 0.025. The carrying capacity is 800,000. If fishers fish at a rate of 20,000 fish per month, write an equation modeling the population. So our logistic model equation was given by dp dt equals rp times 1 minus p over k. Now we're given that r equals 0.025 and k, I'm going to do everything in thousands, so I'm just going to say k equals 800. I'll make a note here that this is in thousands. Okay, so right now we have a model for how the population would grow without any external forces such as the fissures. If we were to factor in the fissures, so I'm going to write dp dt due to the fissures, or due to the fishing, I guess, that would equal negative 20, because the rate of decrease of the population would be 20 per month. So now, in order to find the total change in the population, we'll just add those two together. So our true dp dt equals, I'm going to plug in my values for r, and that's p, 1 minus p over 800, and then finally subtracting 20. And that's our model for the population.